Hello and welcome to Realms Explorer. Today we will explore what exactly a black hole is, how can black holes be created and how many types there are. We will also look deeply into some quantum mechanical aspects of these spectacular beasts. In simple terms, it is merely a region in our universe, or rather spacetime, from which nothing, ranging from normal matter to even light, electromagnetic radiation, can escape. This is because the gravity within a black hole is so strong that spacetime is deformed enough that nothing can jump out. The singularity and as a result black holes are predicted by Einstein's general relativity. The first black hole to be identified was Cygnus X1 in 1971. On a side note, in a very plain manner, what I mean by deformed spacetime fabric is that according to general relativity, all mass affects spacetime. That is, in rash terms it curves the spacetime towards itself, and in the case of black holes this is so pronounced, that no amount of energy can help anything escape from this deformity. Because, it is simply impossible to even theoretically or physically, cram in enough energy into a particle, for it to possess enough energy to leave a black hole. This is an almost elementary description, for it is only when you truly understand relativity, start to see the world lines, and how they are affected by mass, can you understand accelerations in terms of spacetime curvature. I like to think of gravity not as a result of curved spacetime, but simply as curved spacetime itself. The two most unmistakable parts of a black hole are the event horizon and the singularity. An event horizon is the boundary or point of no return. After something, or rather anything including light, crosses this point, it can never escape the black hole again. The event horizon was named as such because, if any kind of event were to occur within this boundary, information from that event would never cross the boundary. By information, I mean radiation, particles, or anything really. For example, how do we know if a person moved in front of us? Light reflects from the person and falls on our eyes to elicit signals in our brain, hence we see the person, in this case the light, or in other words radiation, is responsible for transmitting information about the change of state of the person. This is not possible for an event inside the boundary, as nothing, not even light related to that event, can come out to reach an observer outside said boundary, making it impossible for us to know whether anything even occurred inside. For an analogy, imagine a large river flowing downhill. Now imagine yourself swimming against the current. As the slope gets steeper and steeper, you would need to spend more and more energy to swim upstream, but there comes a point where even at your highest capacity, you're still being swept downstream. That is your point of no return. Now if you substitute yourself for a light particle, and the river for a river of spacetime, the point of no return for light is the event horizon. Now, remember, my own point of no return could be millions of kilometers away from the black hole, and I could name that point human horizon. I apologize, that was a very bad joke. But back to the event horizon, because light can convey information about events occurring, the point of no return of light is called the event horizon. This is part of the reason why black holes have remained an enigma to this day. A singularity is much more complicated, as there are several types. And as if that were not enough, we have never actually reached a consensus on their nature, and if they actually exist with a physical form. In the simplest terms, it is all the mass of a black hole concentrated into a single point at the center. We will, of course, explore the other types as we get further along. One feature of singularities is that they have zero volumes, meaning it has infinite density. This will become interesting when we discuss rotating black holes. How can black holes be formed? The most common method that we hear about all the time is gravitational collapse. This happens when a star's internal pressure is too low to resist its own gravity. The fusion reactions, occurring inside the core, generate radiation which exerts radiation pressure towards the outside, as the energy and particles released travel towards the surface. This is what prevents your average star like our Sun from shrinking due to gravity. As a star exhausts its nuclear fuel, not only does this outward pressure decrease, but so does its temperature. A low temperature means that the particles have lower kinetic energies, meaning they can easily be pulled towards the center due to gravity. which often results in the formation of compact stars like neutron stars, white dwarfs, etc. This collapse can be stopped by the degeneracy pressure of the star's constituents, which we will discuss in a short while. The type of compact stars formed depends on the mass of the remnant, that is, the matter left over after the outer layers of the parent star have exploded in a supernova. If the mass of the remnant exceeds 3 to 4 m0, where m0 stands for solar mass, the mass of our Sun, even the degeneracy pressure of neutrons is insufficient to stop the collapse, and it collapses into a black hole. It has been theorized that if a neutron star cannot form and it still continues collapsing, in rare cases, the quark degeneracy pressure may be enough to result in the formation of a quark star, though this has never been confirmed. There are a few objects astronomers suspect might be quark stars, such as RxJ 1856.53754, 3C58, XTEJ 1739-285, but none are confirmed. Well, what does degeneracy or degenerate matter even mean? It's nothing but normal matter which has lost structure and degenerated into its constituents, like atoms getting dissolved into neutrons, protons, etc. What this means is that the forces of attraction, repulsion, etc., arising due to the electromagnetic and strong forces, have been overcome. In other words, there is no potential energy, there is only the kinetic energy of the constituents now. As the potential energy in the form of electromagnetic, and in some cases strong force bonds, has been overcome, and the bonds broken. To understand this, we have to go back to the Pauli exclusion principle. It states that no two identical fermions can occupy the same quantum state. Fermions are subatomic particles, with half-integer spins. They don't include mesons, which are composed of two quarks, thus granting them an integer number spin. Now, you may wonder why that is. I mean, why cannot they? And the answer is information conservation. One of the pillars of our universe. For example, if you had two electrons that originated from different processes, occupying the same quantum state, at some point of time, and if you were an observer after that point of time, you can never tell which electron came from where, or what process the electron experienced, because for all we know, both electrons might have experienced the same or different past events before they shared a state. After they shared the same quantum state, we can't tell which electron was which, and their different pasts lose meaning. In other words, their past ceases to have meaning or existence. There was previously a distinction between these two particles, but after they shared a quantum state, the distinction was lost. Even though they're still two particles, information in the form of that distinction has been lost. You see how weird that sounds, and it appears that this is a serious violation of our universe. Well, except for black holes, where, as you can see, everything collapses into the singularity. Meaning there is loss of information, and this has been named the information paradox, because no matter what falls inside it can only contribute to the mass, charge, or angular momentum due to rotation of a black hole. Because those are the only properties a black hole could possibly have. Stars are nothing but big balls of plasma, and when plasma is cooled, meaning the star's running out of fusion fuel, and put under increasing pressure of compression, which in the case of a star is simply gravity, it will at some point become impossible to compress further due to the Pauli exclusion principle. The reason being, in this highly bound and compressed state, since there is little to no extra space for the particles to occupy or change their position, a particle's location becomes highly defined. In other words, the uncertainty over its position is greatly reduced. Now, according to the Heisenberg uncertainty principle, what this means is that the momentum of the particle becomes highly uncertain. Therefore, even though the plasma is cold, these particles on an average possess very high velocities, as momentum equals mass x velocity, and conversely very high kinetic energies. Large kinetic energies in turn mean that, in order to compress the object any further, huge forces are required to control the particle's momentum, thereby exponentially increasing the gravity required to further collapse the star after neutron degeneracy sets in. The degeneracy pressure is not due to fermions trying to occupy the same state, but their inability to do so, resulting in very high momentums due to the Heisenberg uncertainty principle, which makes it harder for gravity to collapse the star. In very simple terms, Pauli exclusion principle means you can't simply stack on or superimpose matter onto itself. And if you want to fit in more, you have got to make use of all that empty space in between nucleus and electrons of an atom. The force that's stopping you from doing this, which is essentially the electromagnetic force, and in some rare cases the strong force, is the degeneracy pressure. Imagine you have two magnet bars. You would want to place them as close as possible to save space, and you had to place them with the like poles facing each other. You would either have to apply a lot of continuous force to keep them together, or just heat them to a temperature where they lose their magnetism, which is permanent. That's what it means to overcome the degeneracy pressure. Pardon my poor skills, but this is how overcoming degeneracy can help. You see all that extra space in the second box, meaning now the body can be further compressed. Other ways black holes can form would be as primordial black holes. In the universe, a short while after the Big Bang, since the density was too high, a black hole could be formed directly if a local change in density occurred. In more scientific terms, a density perturbation, courtesy of quantum fluctuations. If it were to have uniform density, matter would not bunch up as gravity would be same in all directions. For our current world to exist, there must have been perturbations in the density that would then automatically cause matter to clump together, as gravity would be different in different directions and regions. One other way a black holes could form would be through particle collisions. This is an exciting possibility, still speculative, that could, if possible, allow us to create micro black holes in our particle colliders, which has an immense practical value. It all boils down to the fact that, theoretically, black holes can be formed if the collisions have an energy density high enough. Don't worry though, even if we created them, they would evaporate within fractions of a second. They won't continue to grow and devour our world. This isn't a joke. Apparently this thought was what caused some people to oppose increasing the sizes and capacities of our colliders many years ago. And of course, lastly, black holes can also form due to mergers of huge stars in a binary orbit, or stars preying on other stars, etc. Hope you enjoyed that. Next time on Realms Explorer, we will explore the different kinds of black holes and some of their sci-fi properties you might never have heard about.